In this video, I'll discuss how elliptic curves are used in an asymmetric key exchange protocol to provide a means to send encrypted data. From my last video, you should remember that we can produce cyclic multiplicative groups in a finite field with modulus p so long as the generator is coprime with p. The Diffie-Helman exchange is going to use this principle as follows. We choose a generator G that produces the cyclic group under modulus P. Alice will compute her secret key A within the order of the group that is generated by G, and Bob will compute his secret key B within the order of the group that is generated by G. They both compute a public key to share, which is G to the A for Alice and G to the B for Bob. Now, both Bob and Alice have the necessary numbers to compute a shared private key, which would be G to the AB. And since the group generated by G is coprime with the modulus, we know that there exists a multiplicative inverse of each element of this group generated by G. So G to the AB has a multiplicative inverse, and we can solve it by getting G to the minus AB. Then we can use G to the AB as the shared secret for encrypting messages, and G to the minus AB for decrypting messages. The public key is composed of the generator G and Alice and Bob's own public keys. This means that the security of Diffie-Helman is based on the difficulty of performing a discrete log on G to an exponent to solve for said exponent. Given the information G, G to the A, and G to the B, if we were to uncover a secret key A or B, we would need to perform a discrete log-based G. And this problem is comparable to the RSA problem for integer factorization because the general field sieve algorithm can be applied to both. Elliptic curves take the form y squared equals x cubed plus ax plus b. If we are going to use elliptic curves for cryptography purposes, we want to have an operation defined on these curve points that abides by abelian group properties. We can define addition on curve points to satisfy an abelian group operation. We know that elliptic curves will have a third point of intersection when we add two distinct points, as you can see if we were to add points P1 and P2 in the following diagram. We define the addition as solving for the third point of intersection and reflecting it across the x-axis. To do this, we would set the equation for the line that intersects the two known points equal to the curve. And then, in the resulting equation, we could factor to find three roots or three intersections between the two functions. We already know the first two, and the third one would give us our x coordinate of the third point of intersection. We can then set up equations for x3 and y3. So the slope obviously is rise over run, so y2 minus y1 over x2 minus x1. Then when we solve for x3, we get slope squared minus x1 minus x2. And when we solve for y3, we get slope times x1 minus x3, and all of that minus y1. We also have to account for the case where a point is added to itself. Our slope equation would have a 0 in the denominator, and so instead we define the slope when you're adding a point to itself as the tangent to that curve. And so we take the derivative of our elliptic curve as the slope, where x3 is slope squared minus 2 times the x-coordinate of our point, and y3 equals slope times the x-coordinate of our point minus x3 minus y1. Finally, we need to define an identity element. So we call this the point at infinity, or O. The properties of the identity element must hold that P plus, where P is some point on the elliptic curve, P plus the identity element yields P, and P plus minus P yields the identity element. Now you can probably see where this is going. If we are able to produce minus p given a generator p over addition, then we've confirmed that we've created a cyclic group, because then when we add p one more time to minus p, we would get the point at infinity, and finally one more addition of p will bring us back to p. And so these cyclic groups, as we have seen before, for group operations could be used in a Diffie-Hellman exchange, where we're using scalar multiplication instead of exponentiation. Scalar multiplication of elliptic curve points can be done much more efficiently than a brute force addition of your generator point p, sum the scalar amount of times. So we leverage powers of 2 in the binary representation of the scalar multiplier. This is known as the double and add algorithm. To multiply a times an elliptic curve point p, we move through the scalar a from least significant bit to most significant bit. The algorithm will update the result in temporary variables with the double and add algorithm described here. When the bit is a 1, we'll increment the result by the current value in the temp variable, and each update will multiply the temp variable by 2, or add it to itself. I'll run through an example of this, and you'll see how the temporary variable keeps the value of the bit associated with the next bit in the loop, and the result contains what needs to be added as an offset to temp to produce the new result if the next bit were to be a 1. So for the example, we'll choose a to be 21. On the left column, I'll show the bits of a. In the middle, I'll show the result, which starts as the point at infinity, and the temporary, which starts as the generator point p. Bit 0 is a 1 in the number 21. So to the result, we add the temporary variable, which is p, to get p. And we double the temporary variable to get 2p. That is to say, if bit 1 now were to be a 1, we would want to add 2p to yield 3p. But bit 1 is a 0, so the result stays as p, and we double the temporary variable because the value of the next bit is 4. And so now we see that bit 2 is a 1, so we add 4p to p to yield the result 5p. And the value of b3 is 8, so we double our temp again to get 8p. In the next iteration, we see b3 is 0, so we don't update the result with the temp variable, but we double the temp variable because the value of bit 4 is 16. And finally, when we add 16p in the temp variable to our current result 5p, we get the final result 21p, and we would update the temp variable one more time, but the loop will come to an end. We want to fix our elliptic curves over a finite group. So we call the elliptic curve operation on the finite field fp as the elliptic curve equation y squared equals x cubed plus ax plus b modulo some modulus, which I'm calling p here. Now, together with our point addition that we have defined in the previous slides, we have a finite abelian group. The fundamental theorem of finite abelian groups states that any finite abelian group can be expressed as the direct sum of cyclic subgroups. And by this definition, we know that our elliptic curves over finite fields are cyclic or contain cyclic subgroups. The proof of this comes from the field of study of abstract algebra, which I don't want to go down that rabbit hole for the purpose of cryptography. But for the purposes of cryptography, what is important is that we've just created a cyclic abelian group with the addition operation using elliptic curves over finite fields. The process of performing the elliptic curve Diffie-Hellman exchange is as follows. We pick a generator point G in the elliptic curve. Alice picks a secret random A within the group order and sends Bob A times G. Bob also picks a secret random B within the group, and he sends Alice B times G. Together they compute the shared secret A times B times G without ever exposing their secret keys A and B. The elliptic curve discrete log problem depends on the hardness of being able to perform division on elliptic curve points to determine the scalar multiplier of the generator. To get A from G times A, there is no known algorithm that can compute this efficiently. In fact, the general field sieve algorithm doesn't apply to elliptic curve point division. The best known algorithm is Pollard's row, which requires a search space equivalent to the square root of the group order. So if we compare the reduction of search space from the general field sieve versus Pollard's row, we'll see that elliptic curves allow for much smaller key sizes than for the same security strength as would be required for RSA or the Diffie-Helman with multiplicative groups. And this can be seen in the table.
Okay, so I've set up a Python script that's going to do elliptic curve encryption and decryption so that I can send messages one way from an encryptor to a decryptor. The elliptic curve I've chosen is SecP160K1 from this resource here. The curve parameters just defined in global variables. The decryptor private key, I'm using just a random bit string that's within the max bit length of the modulus, and I need to make sure that's also less than the group order. So I'll regenerate it if it's outside the group order. Then the decryptor public key becomes your group generator point multiplied by your scalar decryptor private key. For the encryptor, I'm just randomly generating only the private key because I'm only sending messages from encryptor to decryptor for this example. Otherwise, you'd also share the encryptor public key so that the decryptor could know the shared secret for encryption as well. Then in this loop, I'm going to read from the user and send the user's string message across as ciphertext. The ciphertext that requires me to translate a character into an integer, then translate an integer into an elliptic curve point, and then translate the elliptic curve point into the encrypted ciphertext elliptic curve point.
So the functions I'm going to need to implement. First, a fast power algorithm. This, in my last video, I forgot to do. I just did a brute force power algorithm, but was using short keys, so it didn't take too long. But I'm going to use exponentiation by squaring. There's a Wikipedia page that explains this algorithm fairly simply. So this is quadratic residue helper, is basically just, since this curve I've chosen has a cofactor 1, we know the entire elliptic curve is one single cyclic group. The points on it create one big cyclic group. So to check if a given x coordinate produces a valid point on the curve, that is the y squared associated with it is a quadratic residue. The p, the modulus for this curve, is congruent to 3 mod 4, which makes that calculation pretty easy. You just need to make sure that your y squared value when raised to p minus 1 over 2 does not produce p minus 1. So the algorithm to create from a plain text integer, so I've already translated a character to an integer, and now mapping that to an elliptic curve point, basically just need to generate x coordinates until we find a valid curve point. But what if the plain text integer doesn't give us a valid curve point? So the process here is to give us, I'm just randomly using 8, but 8 extra bits of wiggle room where you can continuously increment the bottom 8 bits of x until you get a valid curve point. And then when you decrypt, you can just drop those bottom 8 bits that were used to increment until you received a quadratic residue on the curve.
So while this arrow is going to hold the bottom 8 bits of my number, while it is within the range of an 8-bit number, so 2 to the 8 minus 1, we will check if y squared, which is just the output of our elliptic curve math, x cubed plus ax plus b plus 1p. If that is a quadratic residue, square root y. And this can be efficiently computed because p is congruent to 3 mod 4. Otherwise, the increments are out, and append back to the lower 8 bits of x.
Now here's my encryption and decryption algorithms that are just using these helper functions to encrypt a message with the encryptor's secret key by multiplying by that scalar, and the decryption, which will get the ciphertext and subtract the shared private key from the ciphertext. So we'll define our add points method. We need to make sure that the second point, because the way I'm doing the decryption is I'll subtract the private key. I'll subtract the private key from the ciphertext that I've gotten. I'm going to need to essentially pass the y coordinate as negative because that's how our addition law works over the elliptic curve. The additive inverse is just a reflection of the y. And so if it is less than 0, I'll just convert that into the number field again by adding the modulus. First thing we check is if we're doing point doubling. This means the slope equation is different. It's the tangent. 3 times x squared plus a divided by 2y, which is the mod inverse of y, of 2y. The mod inverse function I'm using in Python 3.8, you can just use the pow function with your modulus, and the multiplicative inverse will give you will be given when you pass a -1 in the exponent. Check for some edge cases if we aren't point doubling, where the points are different, but one of the points is the point at infinity, which I've defined as 0, 0. So if x0 equals x1, this basically means that you're adding p with minus p, because we've already checked that y0 does not equal y1. So we would yield the point at infinity. Otherwise, if the first point is the point at infinity, then we just return the second point, because a point plus the point at infinity is the point. And the same goes for if the second point were to have been the point at infinity. Finally, we have our regular point addition. Our equation for slope is rise over run. And now the lambda is the computation that needs to be done dependently on whether we're doing point doubling or adding two distinct points. The x2 and y2 equations can be done for both in the same way once you have computed your lambda or your slope. So lambda squared minus x0 minus x1. In the case of point doubling, that's 2x0. y2, we have x0 minus x2 that we've just computed, times our lambda minus y0. And now let's do the double and add method, the efficient one, where you leverage the binary representation of your scalar multiplier. So I'm going to convert the scalar k into a binary number, actually a binary string using the Python bin function. And note that this will create a string of bits, but it has the first two characters as 0b, and then you get your binary representation. So I will chop those off of this binary string. First two are gone. Now we'll iterate from LSB to MSB. So we'll reverse the bit order. Check if the bit is a 1 character. Remember from the algorithm, this means we then add what is currently in our result. So our result is the first point to what is currently in our temp, using our point addition helper. And each time we update temp. By doubling it. And return our result. And now we've implemented all the functionality to encrypt plain text into a ciphertext that is a point on an elliptic curve that we have chosen, and then decrypt it as well. So let's run this program. Start with the message hello. Each plain text maps to an elliptic curve point with an x and a y coordinate. Then we create a cipher point out of this plain text point. When we're ready to decrypt, we'll hit any key and we should see hello. And as you can see, we have deciphered each character back into the points on the elliptic curve. We take the x coordinate, we drop the bottom 8 bits, and then we can convert that integer back into an ASCII character to get actually I think I'm using UTF-8. Yeah, and we'll get the associated character. Let's encrypt another message. We put AM34. And we receive AM34. And the string to break out of the loop is exit, so we'll encrypt exit, send it through, and the program ends. Thank you for watching.